Hi there, my name is Christopher Worst. Welcome to video 4 of Homework 6. It's asking us to use the Radford-Rice equation to perform a fixed temperature pressure flash calculation for a feed of 4 moles of benzene and 6 mole per second of toluene with a flash drum set at 393 Kelvin and 150 kilopascals. Then asks us what the compositions and flow rates of the outgoing vapor and liquid phases are. Now I've got my notes to the side here. Let me flip them over, get the actual equation up. Good. Let's get started. So we're going to be using the same collaboratory script as we used for part 2. Hello, our beautiful graphs. And to start, we're going to need to create a variable, much like x and y in the last one. We're just going to name this z because we don't want to rename anything. We're going to need to make a NumPy array of the flow rates of both of the components. So we and I'm also going to make sure that I'm going to restate to the temperature. It's 393 Kelvin. Nope, not bit length. Pressure is equal to 150 E3, 150,000 pascals. And with that, am I missing anything? I don't think I am. I don't believe I need to make any new, variables for our equation, so we're just going to dive right into the function. Actually, wait a minute. Yes, I do. Sorry. We do know, if we remember our equation, we remember that K is equal to the vapor pressure, P dot P vap, divided by our normal pressure. So I'm just going to add spaces there. And then we also know that we want our total moles per second, our total feed line speed to be, let's say, 10 moles per second. All right, now that we're there, we're able to define our Radford-Rice function given our z, not our z of our, just a vector of unknowns, and I also forgot in my zeal for coding, I forgot to put the temperature there. That wouldn't have run and would have been a bad error. Either way, we have that now. So we have our vector of unknowns. Our first vector of unknown is going to be VF. Remember, if we look back, that's that V divided by F, because that is the only thing that we're missing in our summation. So it's going to be vec of 0, vec 0, the first value in our vector of unknowns, and really the only value in our vector of unknowns. So, with that being said, we can simply return the sum, so numpy.sum, of what is our equation, z multiplied by k minus 1, divided by 1 plus, and this is VF times, and this is k minus 1. Okay. With that, we should be able to shift enter. There are no immediate errors popping up. And if I were to return RR given a vector of VF of, say, I don't know, 0.3, float is not subscriptable. 3. Int is not subscriptable. It's not the biggest issue. Either way, x0. It's not overly it's not a big issue. And much like, hello TripAdvisor. Get off my screen, thank you. And remember, for the root function, we're going to want to excuse me, we're going to want to have that as an array. So first and foremost, we're just going to root out our equation because we want our VF value, and a given guess of, who knows, 0.5, and we want x and 0, the first value in that array, but we want to root this out because by rooting it out we can find that vapor fraction, and by finding that vapor fraction we can find everything else. So shift enter, runs fine. Let's double check what VF is. It is 2.4, and I'm not sure why it's not giving us that in the first place. Maybe I should erase these. No. Either way, it runs fine. 2.486 is the that vapor fraction. Now, if we can find the that vapor fraction, all right. So now that we have VF and it's given us a value, so at least everything's running. Whether or not it's running correctly, we can find out later. We can find, we have VF, we can find the value, the number of moles coming out of the vapor phase, we can find the number of moles coming out of the liquid phase, we can find the number of moles in the liquid phase per component, and then we can find the number of moles in the vapor phase per component. So let's start with V is equal to VF times F, because remember VF is V divided by F, so V times VF times F is that vapor phase, it's a vapor phase fraction times the total number of moles to get the number of moles in the vapor phase. L is going to be equal to, remember, F is the number of moles is equal to the vapor plus the liquid. So liquid is equal to vapor, total number of moles minus that in the vapor phase, not value error, thank you very much. Now that we have those two, we can find what x is, and we know that x is equal to z divided by 1, whoops, I need to, 1 plus VF multiplied by k minus 1, because we figured that out earlier, and remember we substituted that into this Rashford-Rice equation. So now we have that, and remember just y is equal to, and due to the substitution that we made earlier, y is equal to k times x. Shift enter, no errors immediately popping up. Now we could just run a few print functions, so vapor phase vapor liquid ratio is equal to, and remember we want VF, and I'm going to put a function in here. Good. And let me just double check that real quick to make sure that I have that right. Good. Yes, okay. And then I'm just going to copy and paste this for F, L, V, X, and Y. So we're going to have 1, 2, 3, 4, 5, 6 total. So we want vapor-liquid ratio, we want moles in vapor phase is equal to V. L is the moles in liquid phase. We don't need this last one. We have X here. X is the moles per compound in, and this is in the liquid phase, and then Y is moles, or mole ratio, of compounds, and then this is mole ratio of compounds in vapor phase. Shift Enter. All right, now we have some values, and now if you look at this, it seems odd. There are 24 moles in the vapor phase and negative 14 moles in the liquid phase. That shouldn't be possible. Funnily notice, however, that these two add up to 10. So the total number of moles in vapor phase and moles in liquid phase will add up to our F value. But this vapor-liquid ratio we want to be somewhere in between 0 and 1. Now it's at 2.4, which shouldn't be correct, which means that our initial situation is not quite working right. So if we modify the temperature or the pressure or both, and we could kind of fine-tune it to make sure that it works correctly. So what if I make this 180,000? Good. This turns into a vapor-liquid ratio of 0.545. That means for every about 5.5 moles in the vapor phase, there's going to be 4.5 in the liquid phase. You can see that here. So there's 5.45 moles in the vapor phase, 4.54 in the liquid phase, and then below that you have the mole ratio of the compounds in the liquid phase. So out of this 5.5 moles, about 30% of that is benzene, about 70% of that is toluene. Out of the 4.5 moles in liquid phase, yes, or the 4.5 moles in liquid phase, 30% of that is benzene, 70% of that is toluene. In the vapor phase, out of the 5.5 moles, 50% of that is benzene, 50% of that is toluene. So, with that being completed, and with the initial values and initial situation being modified to get a correct situation, we've done what the homework is asked. Thank you very much for watching. I hope you have a wonderful day.